Hi, welcome to Unit 35. In this unit, we're going to talk about the origins of the solar system. Unit 34 hinted a little bit into that, basically, when we looked at the structure. So first of all, we're going to determine the age of the solar system using basically properties of radioactive materials. And then based on that, we're going to see how the solar system was estimated to be about 4.5 billion years old. And then describe the solar nebula theory. That's basically how the solar system formed. Okay, that's actually the most reliable theory right now based on current observations. And explain the different elements condensed at different. So that explains actually how the solar system formed. Why the inner planets are rocky. Why the outer planets, for example, are gas. Okay. And then discuss how planets form and differentiate. Also, that gives me an idea of the inner structure. Again, most of these things were hinted in Unit 34. Radioactive materials is an intrinsic properties to materials. Some materials are radioactive, and when they are radioactive, they're basically the amount of that material that basically what radioactivity is. It's the emission of either gamma particles. That's really an instability issue that the nucleus of the atom basically was not stable. So the rearrangement of the protons and neutrons, which allows it to be more stable. The gamma emission does not change the nature of the object, so it stays the same. Exclude that. Then you have two other kinds of emissions, namely the alpha emission and the beta emission. The alpha emission, which emits basically hydrogen, helium nucleus, then in this case will result in a complete different chemical element. Okay. You're looking at an element in the periodic table that has a given number of protons. Those protons, two of them will escape with the helium nucleus. Two hydrogen atoms will escape in addition to two neutrons. So a total of four nucleons escape. So you're left with a number of nucleons. Number of nucleons which is down by 4, but the main thing is the number of protons is down by 2. Which means that the element will move 2 scales on the left in the periodic table and become different. For example, and that's probably not the case in this case, if you have oxygen and emits alpha particle, which is probably doesn't, but the best example is polonium, but polonium is not a common element that is known at least on a daily scale. So let's for a moment think that the oxygen went radioactive and emitted an alpha particle. In this case, the two protons that it has in it will change with two more neutrons and move to carbon. So completely different elements. You go from oxygen to carbon, which is completely different chemistry. The same thing with the beta emission. In the beta emission, basically what you have an emission of an electron, okay? Most likely, most of the time, it's a positron. Sometimes it's actually a pure electron. A positron is just a positive electron. So if it's a positive electron, that means we lost one proton. Again, if it was oxygen, it moves to become nitrogen, which is completely different. Okay? Albeit it's heavier nitrogen, but it's still the same nitrogen in terms of chemistry. Or it could go basically emit an actual electron. In this case, the number actually increases from 8 to 9. Okay? So again, these two types of emissions, which are naturally occurring for some of the elements, they can change the chemistry. So we have what is known as the parent, and we have what is known as the daughter. So the parent is the initial element, and the daughter is the final product. Granted that the daughter itself can become a parent and generate a new daughter, and so on and so forth. So the cycle can be very, very long in terms of radioactivity. Each process is characterized by what is known as the half-life. Okay? Half-life is the time it takes for a certain sample to shrink by half. And this depends on the material. So the fraction, for those who are more math inclined, is given by this expression, 1 over t to the power of t over tau, where tau is half-life. Okay? T is the time. So I generated this GeoGebra simulation that gives me basically different values. Let me hide this thing in here. So it gives me different values for tau, the time in here in this case. This is 10 years, for example, and the fraction initially it's at full 1 at t equal to 0, and as time evolves, Once we reach 10 years, the fraction drops by half, because half-life in this case is 10 years, okay? T equals to 10. This is T, okay? So in this case, its value is 10. If I move it to 20, then in this case, after 20 years, it drops by half. So what happened after 40 years? It drops by another half of half, which is a quarter. What happened after 60 years? There's another half of half, so it's going to be dropped by 3/4, and then we're left with only 3/4 in this case, which is 12 and a half or something like that, okay? And then percent, that is. And then after another quarter, so it's going to be quarter of the quarter. Sorry, let me repeat that, okay? Half of the half, which is a quarter. Half of the remaining basically quarter, so it's going to be an eighth, okay, and so on and so forth. So it's always half of a half of a half of a half, how many times you have, okay? So if I go to T equal to 100 years, obviously only after 100 years before the first half is gone. Some of these elements are in the billions of years, so it takes 1.2 billion years for half to be lost. So if I go to a sample, and I know the daughter and I know the parent, and this daughter could not be formed except through this process. Measure the amount of the daughter versus the amount of the parent. And if I know it takes 1.25, for example, billion years for the daughter to form, half of the initial amount of the parent, then in this case, and if I find, for example, it's 1/8. So I know 3 generations have already passed, 3.75 billion years. And that's how the estimate, that's how the Earth, I'm sorry, here on Earth, actually, you have to be careful on Earth because there are other processes that form materials. But if you get it from a meteorite, for example, on Earth, then you know that meteorite is most likely unchanged from when it formed during where the solar system formed. And that sample becomes a very good sample to determine the age of the solar system. That's why meteorites are valuable, because they help scientists determine the age of, among other things, the solar system, including Earth. So this is the value of the solar system. Again, in here, this is the same graph I drew in here for potassium. Potassium is known to have a half-life of 1.28 billion years, actually. So after 1.28 billion years, you will have half of the original amount, okay? After 2.56 billion years, the potassium that you have in the sample should represent half of a half, basically a quarter left. Now the daughter in this case, which is another element in this case, calcium. So calcium will grow, but because I'm producing not just calcium, calcium itself is producing another element, in this case argon. So I have, or at least the combination of the two, I'm sorry. So the argon also is formed. So in this case, I have to be careful. So, but if I focus just on the parent in this case, that gives me a good indication of the age of the sample, okay? This curve in here. So after 2.56, after 3.84 billion years, I know how much of potassium I have. After 5.12 billion years, which is not yet there yet, we know this is probably somewhere in here today, about 4.5 billion years. That's how we know how old the solar system is. Just take a sample, hopefully of a meteorite, something that was not changed from when the solar system formed, and find the ratios. Once you do, you know how old the solar system is. So this is a technique to determine the age of the solar system. Now, anything that we're going to explain the solar system formation must account for the fact that the solar system main planets, including the sun, are on the ecliptic, the rotation speed, and the rocky inner structure, and basically the gas or the less dense materials for the outer materials, and so on and so forth, that we talked about in Unit 34. So the solar nebula provides a powerful theory for that, okay, that somehow when the solar system, before it was formed, there was a huge amount of gas and dust extending the length of 3 light years. Basically, the radius of the region where the sun is, times 2, okay? That material was large, of course, a huge quantity, but it's spread thin. Due to the forces of gravity, the material starts to clump together. first of all, the more dense materials, namely iron and nickel. And once they are dense enough, they form the nucleus, if you wish, of a planet called the planetesimum. Okay. For the inner planets, it has to be rocky. For the outer planets, now the ice starts to form. So that's basically the basic idea. Now, gravity works actually at an accelerated rate. The more you have, the more stronger it is. Remember, it's proportional to the mass. So the more you have mass, the stronger it becomes. So it's going to accelerate. The process takes actually not that long. Initially, it takes a long, long time, and then it accelerates, okay? So the condensation process is similar to what happened in a kettle, for example, when you let go of it. The materials that condense at lower temperatures, they condense at lower temperature because the steam, as it escapes in here, it's hot in the bottom and low in the regions that are far away. And that's where the condensation happens, okay? So again, the condensation is a process that is related to temperature. And if I look at the materials in here, starting from hydrogen, for example, its condensation temperature around 180 Kelvin. So that's a reminder, Kelvin is 0 Kelvin is around negative 273 degree Celsius. So when I say 180 Kelvin, it's still a negative temperature compared to the degree Celsius, okay? So it's a very, very cold temperature because at 273 Kelvin is when the water freezes, is 0 degrees Celsius or 32 degrees Fahrenheit. So for helium, it's even lower, 3 Kelvin. Helium and neon and argon, they are actually, they have very low condensation temperatures because of the fact that they are inert gases, okay? You have carbon at 80 Kelvin. This is actually in methane. You have nitrogen in NH3, also at 130 Kelvin. Those are very, very low temperatures, by the way, okay? And then nitrogen, actually gas, nitrogen is used for fast freezing of food, basically. And then you have oxygen in the silicate form, basically when it's combined with silicon, which is rock, okay? The everyday rock. It's 1,300 Kelvin, but it's pure oxygen, it's around 180 Kelvin, okay? Neon, as I mentioned, is at a very low temperature. Silicon and oxygen, they form silicates. That's basically the different forms of oxides of silicon. And then you have iron around 1,400 Kelvin. Note the temperature. This is in conformity with the way that the planets are lined up. So Mercury, iron. Then as you start to go higher and higher in temperatures, remember, you go 200 Kelvin, 300 Kelvin, that's room temperature, basically. That's where the silicate starts to condense. Because inside the planet itself must be super hot. Because the materials, as they get closer and closer, because of two main reasons. First of all, more friction as they get very close from one another and they don't jump. I'm sorry, cat wants to jump on the table. Anyway, so as they get closer and closer, they hit more another, so the friction will increase their temperature, number one. Number two, also, because these are radioactive and radioactivity produces energy, and that's how actually the Earth kept its heat in the core. So the temperature being so high will ensure that the silicates starts to condense. Remember, the condensation for this material is around 1,400 Kelvin. So iron and silicates start to form up to the asteroid belt. Then the water, H2O, which is room temperature. H2O is 0 degrees Celsius, okay? 273 Kelvin. And then ammonia and the different structures. And this explains more or less the structure of this planet based on their densities, remember, from Unit 34. So again, the theory goes that the planetism was formed first. These are basically the gravity starts to get tiny, tiny particles together, and then they start to grow. And time, as I said, accelerates. So the whole process is super fast, relatively speaking, compared to the age of the solar system, okay? And then, obviously, the inner planets, they are mainly rocky planetesimals, and the outer planets, they are mainly water planetesimals, okay? When they condense because of the different temperatures as they are far from the sun. Once this planetism was formed, then the process accelerates. They gather more and more materials around them, okay? And they become protoplanets, really. And this protoplanet starts to heat from the bottom because of the two processes I mentioned. And now another process starts to form. The heavier, the denser materials, I should say, starts to sink in, and the lighter material starts to go up. Okay, this is a process that is known. If you take, for example, a clump of material that's super dense and put it in water, it's going to sink in because of its high density. This is also true for all of these planets. So the planets that start to form, so the more dense materials go inside, namely the iron and nickel and all of those materials, and the lighter materials, namely the silicate, starts to form up. This is at least for the Earth and for the other planets too. So this process is called differentiation because it's separation of the different materials based on their density. However, this is just basically the structure inside. Now comes the late bombardment state. So basically, at this point in here, more materials are still out there in the solar system. It starts to rain in, and that forms the crust. And as they do fall in, they form these craters and these bubbles that form on the structure in here. So they add more materials to the planet. This process and another process, so because lighter materials, namely gases, were trapped during the formation of this planets, the crusts, so they get released on their own by either volcanoes or any other basically seismic activity inside, and also from the release of those materials when they're impacted by those late state bombardment stage that I was talking about in here, that basically from the rest, so from the solar system. So that forms an atmosphere for these planets in addition to the rocky structure that I mentioned in here. Now, does the planet retain its atmosphere? It depends on its gravity and how close it is from the sun. Okay, if the gravity is strong enough and it's far away from the sun, then there is a chance for it to retain it because of the fact that the temperature will make this gas move more and more. And each planet has its own gravity, which means it has an escape velocity. The escape velocity is actually has a square root of the mass of the planet. Okay, so the more massive planet, the higher the escape velocity. Okay. But it also depends on its size, because if you want to escape the planet, you have to escape it from its radius, not from its core. But if the planet is replenishing its atmosphere, so that kind of compensate for the material that is lost, because the particles in the air, they're moving with random velocities. Some of them are moving super slow, some of them are moving super fast. The average depends on the temperature, though. If the temperature is low, the average is high. That means more of them are moving at high speeds, meaning that they can reach the escape velocity and they will escape the planet. And that's probably what happened to Mercury and Mars, because they have low escape velocity, especially for the case of Mercury, and it's close from the sun. It's high temperature, so its atmosphere is gone, most of the elements. For the case of the Earth, it loses material on a regular basis, and so does Venus. But both of these two are replenishing them. Actually, Venus is replenishing at a higher rate than the Earth does, okay, through the outgassing process. So that's basically what's going on. If the temperature is low, like in the case of the outer planets, I mean, if you ask Pluto, for example, Pluto is super far away that it even atmosphere condenses and becomes actually a solid rock. So if those cases, in this case, they're far away, so the temperature is low, so the average velocity is low, which means there is less chance for them to escape, even the low escape velocities of these planets. Thank you for your attention.